As Karunakara said, we are talking about quality-related issues, and you might think that this is quite boring area in measurements, but I'm sure that it is one of the most important things when doing laboratory measurements, and also when you are doing scientific research. Because if your research has bad quality, so what would happen then? Nobody believes you in those cases. All right. Let's go. I will move this one here. Okay, these are the contents of the presentation. So what is the difference between quality assurance and quality control? Quality management in a laboratory, qualified personnel, working practices, equipment stability, for example, laboratory information management system, LIMS, uncertainty estimation, very shortly in this case. In the next presentation, I will consider this part more detailed. How to prove quality of the analysis methods, and how to prove quality excellence. So just now we are not talking about technical things. We are now a little bit, how to say, higher level. All right. What is QA QC? I took this information from this site. Okay, what is quality assurance? Definition here. It is a set of activities for ensuring quality in the processes by which products are developed. In your case, the product is activity of a sample. However, quality control, it's a set of activities for ensuring quality in products. The activities focus on identifying defects in the actual products produced. So I have to say you that I didn't understood. If I look at only this definition, it's difficult to understand what's the difference there. It's better to have some examples. So here are some other points or differences. For example, here, it's a tool. Quality assurance is a managerial tool, whereas quality control is a corrective tool. I will not go through all these things. I hope you will read these later. You will get all these presentations. All right. There is another www site. So what's the difference between quality assurance versus quality control? So quality assurance is a broad process for preventing quality failures. The QA team is involved in all stages of a product's development. In essence, production, testing, packaging, and delivery. In contrast, quality control is a narrower process. It focuses on detecting mistakes, errors, or missed requirements. So this is quite good description about the process. quality assurance, it's a proactive process, whereas quality control is reactive. All right, let's go on. Perhaps you know that my institution, Radiation and Nuclear Safety Authority, it is testing laboratory. We will be later be as a calibration laboratory. So the accreditation of a testing laboratory proves that the laboratory produces reliable results with the testing methods that are included in its scope of accreditation. The testing method is, for example, alpha or gamma ray spectrometry. So testing is therefore product-oriented, and thus it is in the QC domain. So testing for quality isn't assuring quality, it's controlling the quality. So quality assurance makes sure you are doing the right things the right way. However, quality control makes sure the results of what you have done are what you expected. Let's give an example of that. So, if you are preparing a quality manual, I mean instructions how to operate in a laboratory, it is a QA process. However, if you are constantly measuring background of your detector or full fit, half I mean the peak resolution. So it's a quality control area. I think this is one of the most clearer way to see the difference between assurance and control. All right. Quality management in a lab. So it is composed of many things, starting with very high level, I mean quality policy. System should define very well the leadership, who is responsible of what. Quality manuals must be prepared. And there must be a systematic way to collect information related to quality. Of course, you must obey some standards. This is essential thing. Developing a quality system, it is a continuous operation. In our lab, we are always doing that. And of course, high working ethics and culture are part of the quality management system. And in fact, the responsibility is yours. So, all employees must be committed to keep high quality in their own work. Of course, the biggest responsibility is for the bosses or professors. But the main response is yours. I mean, in practical issues. So, laboratory practices require, for example, high quality personnel, well-defined working practices, good quality equipment. I think you have this kind of equipment here. Appropriate laboratory information management system, LIMS. Uncertainty estimation of the measurements. I think this is more quite routine in your case because you are doing research. You have to validate the methods. And in case of errors and mistakes happen, you must have a policy for that. What happens? Because it's very important to reveal if something bad happens. For us, it's a routine. Really a routine. Perhaps I can say that, okay, now I made a mistake for spectrum analysis, and then we are not looking it in a way that is it you or you that did the mistake. It's not the point. So the point is, what is the reason? Do we have some bad procedures? Okay. Participation of intercomparisons and proficiency tests. It's important. Avanes, how many times per year you participate in intercomparisons or proficiency tests? Around?
We participate in IAE intercomparison exercise every year.
Every year, yeah.
In between, sometimes BRC, the Baba Atomic Research Center, also sends their own intercomparison. It's very rare, but it does.
Yeah.
So, or else, sometimes what happens, this year we are planning to have international radon intercomparison, where samples from around last time they sent it here and we were able to measure it. So minimum one.
Yeah. Okay. Nice. Also, continuous development of work and working practices, it is important. Now I am talking about you. Good quality personnel. So, elements of competence. You must have appropriate education. When you go first time into the job, so somebody must show you briefing, what kind of things you should do. And after this briefing, the new employee demonstrates his or her capability of performing the procedure. And this is important. Continuous learning at work, and this is a standard thing that is used, for example, in university labs, because their main task is to produce PhDs or Master of Science level candidates, and also job rotation. It's a sometimes very good thing. Motivation and ethics, it's very essential. So your well-defined descriptions of the duties is important. Your position must be determined in the quality management system. And this is important, that opinions of the personnel, it's very important. So if you find out some bad processes in the lab, then you have to tell it. You have to tell it to your bosses or professors or directors. And the information flow, it must be active. So if you see some errors in your procedures, then you have to tell it. But of course, the role of supervisors is important. So the typical education in our area, it's a chemistry of physics. We have to understand measuring technology and quality and knowledge of the quality management. So the supervisors, they have overall responsibility for lab procedures and final results. About working practices. So, quality manual or other documentation should cover all working practices. So there must be guidance of the work. Safety at work must be considered. Cleanliness, so that we can avoid contamination or cross-contamination. Precautions for handling of chemicals and equipment. Environmental conditions must be good too. So, as you have here in this laboratory, there are separate rooms for sample treatment or pre-treatment, measurement equipment, and analysis. So it's very important, especially in radiation measurement area, the background must be as low as possible. There must be a backup system for electricity. Do you have this backup system here? What about the lab?
Yeah, this is for
yeah.
This is actually 3 kV system.
Yeah.
And we have a 7 kV system
Yeah.
upstairs. So we get around 16 hours of backup for low load.
Yeah.
And if it is high load around, sometimes during the thunderstorms.
Which you can explain this to whole.
So during thunderstorms, we switch it off in the night and remove the plug so that our systems do not get affected by the thunderstorms. Because even I think it's a very big problem here. Systems don't go shut off. So that is one of the systems that we have. And for the first floor, it is completely separate systems. And then to back up this backup, we have generators. So suppose power does not come within, like let us say, 10 hours or 12 hours, in an unfortunate condition, we can switch on our generators.
All right, thanks. So one point is also that we should, or labs should have continuous monitoring of humidity, temperature, dust, radon, etc. in the lab. For example, this is one part of our lab. This is a gamma ray counting room, and we are constantly measuring, for example, these things. This is also quite important thing that we should not allow all persons to go to lab, because they might not know how to behave in the lab. It is one point. There are several other things that must be taken into account. So it's a more or less security-related thing. And the biggest point is this: everybody must follow instructions. Equipment stability. So regular follow-up is necessary. I mean, detector background, energy resolution, and efficiency. Blank samples should be measured regularly, and following up the performance of the analysis method, it's necessary. And also control charts, including warning and action limits. They are they should be present. Acceptance criteria in these cases are normally set to 2 sigma or coverage factor to 2 as a warning limit and 3 sigma as an action limit. So, for example, in this case, our chemistry team is monitoring Quantulus background, the scintillation spectrometer, this one. So this axis is here, time, and this is count rate. So the background should stay normally between these areas. However, if the backgrounds go there, it's a warning. Perhaps they should do something if the background goes there. And if the backgrounds go there, then they really has to do something. What's going on in your detector? So the most important thing is to know the operation of the equipment. You need to know how the equipment functions. This is the key issue. All right. LIMS system. Some of its characteristics. It should be well described and documented, easy to use and flexible, extensive enough but fit for purpose. It may contain the whole chain of sampling, sample processing, measurements, analysis, and finally reporting the results. Avanes, can you tell all of us what kind of LIMS system you have in your laboratory? I mean laboratory information management system.
We don't have a centralized system as such, but should go by the slide, basically. So we, the normal practice everyone does. We take care of all the field conditions, we take out all data, we write down it, we note it down, and a copy of it is forwarded to the reporting manager and everyone who is related to it. So the first time is have a laboratory manual, one which is called as Karen manual, and also we take manuals from other reputed like Kellogg Soil Survey Laboratory and Environmental Monitoring Laboratory (EML) manual, and we have made our own set of manuals for each data or each analysis. And then once the data is generated, set of results, one of us is going to do it separately so that we can check the quality of the data, and this is sent to the reporting manager and approves it whether this is good or not. So this is kind of a practice we hold, but this is something new for me.
All right. Okay, let's go on. So following the whole analysis process in real time, it is essential. So it's the role of the LIMS system. It should also contain quality control issues, should be well protected, I mean data security, and its maintenance should be straightforward. I will show you some things how we do or what kind of LIMS system we have. We have a system called as NAMIT. It just made web-based software to manage data flow during the fuel analysis chain. So we basically analyze two kinds of samples. So sometimes individual companies send us samples, and they are saying that please analyze the results, and then we do that. But of course, we are doing sampling by ourselves, of course. So this is included, this phase in our LIMS. Sample processing system is there. Measurements, of course, are there. Not only gamma ray spectrometry, but alpha spectrometry, and for example, ICP-MS, mass spectrometer. Spectrum analysis is included that system, and also reporting. So it's in fact very big system. So, and the analysis process is, we can follow it as a chain. So there is a color coding follow-up system. I will show you an example soon. So our system can follow the measurements like this. Here is an example for gamma ray spectrometry. Here are 4 detectors. Detector names are here. The detector status is shown here. This mittauskäynnistä means that measurements is going on in that detector. So we have a sample code. We call it as a NAMIT code. Then the measurement time, and we can see a brief, very small picture of the spectrum, that we can very quickly see that, okay, it's really measuring, and there is a spectrum. So this is perhaps the main window of the software. In this column, there are samples, short sample description. For example, the first sample here is air. Second one is milk. So these 3 columns show that which is the status of the measurement. And for example, in this case, this sample is waiting for the measurement. This column shows that is the measurement ready. And if it is ready, then color is green. As I told you previously, we have automated analysis system for the spectrum analysis. And it is this column here. Green means that automated process was okay. However, in this case, something happened. So there is no automated process. And in this case, we have to check what's going on. After automated analysis, we do manual checks for all the spectrum. So yellow color means that we are waiting for the system is waiting for the manual analysis. This is the way how we can follow our detector calibrations. It's a quite complex picture, but in this case, we have a detector known as B3 and a certain source or sample. This is measurement time, and these are the nuclides present in several of our samples. And these are the activities of each nuclide in a certain reference date. And if we are measuring, this is for year 2015, so almost 10 years old. But according to the color coding, for example, yellow means that, okay, you should check the result once more. For example, in this americium case, the true value is 211, but we obtained in the automated analysis 223 becquerels, as an example. Okay, some nuclides has already dead because they are short-lived nuclides. So this is the way how we follow the calibration correction. Let's go to uncertainty estimation. It's in fact quite tedious and sometimes difficult area, not very easy area. But I'm talking it very briefly. So, relevant thing is that all uncertainty components must be accounted for and quantified. I will show you soon some examples. It requires good knowledge of sources and uncertainties in the sample preparation, measurement, and analysis. And its traceability is essential. So the point here is that a result without uncertainty estimation is not a real result. I mean, in science, of course, in practical life, everyday life, it's not so important. But in science, this is important. And you have to realize also that combined uncertainty is not equal with statistical uncertainty. I will explain this more clearer tomorrow. But this is the thing that we report when we report the result of the analysis. This is just a short example. One of my colleagues did this several years ago. This is an example of lead-210 in radiochemical separation. So there are different things. This axis is uncertainty in percentages, and these are the things that affect uncertainties. For example, measurement, basically it has an uncertainty level of 6%, but it may vary depending on the case. Weighting, by using scales, for example, it usually has a low uncertainty. Pipetting, in fact, I don't know these two, what's this intra and inter, but about the tracer nuclides, and the total uncertainty is around, in this example, it's around 11%. Another example, typical uncertainties in gamma ray spectrometry. This concerns coverage factor of 1, which is in fact the same thing as sigma is 1. Okay, typically typical peak area evaluation uncertainty is around 0.1 up to 30%. In Stuk, we have decided that if peak area uncertainty is greater than 30%, then we do not report that nuclide. We report, for example, minimum activity level in that case. Background may sometimes have a big effect. Full energy peak efficiency 0.1 to 15%, it depends on the energy. Standard sources, their activities are usually very well defined. Gamma ray emission probabilities in a nuclide library, they are usually very well known. However, in some cases, especially when the emission yield is extremely low, it may be up to around 20%. But these are just examples. Okay, this picture is really bad from the visualization point of view. But what I did around 10 years ago, I identified in gamma ray spectrometry many uncertainty components influencing the results of our measurements. And the measurement is done with a calibration source. So the first source here is probably lead 210. Second one was americium 241. Then it goes to the highest energies. This is yttrium 88. These two peaks here, or spots here, they are for cobalt 60. Let's go this case here. So, what happens in the case that if I have a detector here, this one, and I put the source not in the symmetry axis, but it has off the symmetry axis, very small. Distance plus minus plus minus 1 millimeter. In that case, the effect is not very big. Okay, if you go quite top, this means that we do not exactly know what is the sample height. I assumed that the sample height varies plus minus 1 millimeter. Very small, in fact. But the effect of the result is very big. One of the biggest uncertainty components. And in this case, it's a sample elemental composition. So you can see here that, so this number is uncertainty in percentages. You can see that in very low energies, you have to know sample elemental composition to get good analysis result with small uncertainty. And then there is one very complex thing, which is this coincidence correction and its uncertainty, because determining coincidence correction it's not very easy. So there are some nuclides which don't have any coincidence correction, such as cesium-137. So its value, I don't know what is the spot here. Maybe it's this spot. Its value is, uncertainty value is practically zero. But for example, cobalt-60, it has a coincidence correction. You can't see it very well here, but it's this. So the total combined uncertainty, it's this kind of effect for these nuclides. So later, please look at this picture. It is a very bad picture because many components are there. It's difficult to read. But if you follow it, you can understand something more if you look at it very carefully. All right. How to prove the quality of your analysis methods? There are several ways to do that, but intercomparisons or proficiency tests, they are the things, most relevant things. So intercomparisons between different labs. It's a good way to prove quality. Of course, in the case if you have successful results or participation. But in this case, the result depends on the quality of the participating labs. But these proficiency tests, they are normally done by primary laboratories. These primary labs perform or do the samples very carefully. They do many analysis methods in reporting, for example, activities of the nuclides present in the sample, but also other things, elemental composition, etc., etc. So they are very high-level labs, and their results are, in general, you can keep them as correct results. So the result does not depend on the quality of the participating labs. So the sample contains known radionuclide activities with well-estimated uncertainties. But sometimes other issues than the activities are also considered. This is our case. Avane said that they are participating perhaps once or twice per year in intercomparisons or proficiency tests. These are our numbers from 2004 up to 2022. So on the average, we are participating 5 to 6 times per year. So, and this thing, it is written in our quality management or quality manual. It's written there that we have to participate 5, 6, even 7 times per year. I don't now remember the exact number. This is a typical example for us. This is cesium-137, and in this picture, there is a so-called Z-score followed. This is the value of Z-score. Look at here. And these numbers here are the numbers of participating labs. We are located somewhere here. So red colors mean that some labs didn't use very good or reported very good result. However, we have done some mistakes in some cases. So this is not the only case when we got very good result. So this was European Commission organized proficiency test. The sample is mice powder. So this is a proficiency test organized by Comprehensive Nuclear Test Ban Treaty Organization. And these are our results only, and the nuclides are shown here. And vertical axis is the percent of deviation. These red lines, I guess they show the limits. So as you can see here, we are capable to analyze all radionuclides that can be detected by gamma spectrometry. And in one case, this is vanadium 48. There is, I cannot say it's not a mistake. Of course, we have analyzed this, but I don't remember this anymore. So, how to prove your quality excellence? So, it's this process, according to this standard. FINAS is our accreditation body. It's a totally independent body that evaluates us. FINAS also makes accreditation to all labs in Finland in different areas, gravitation, temperature, etc., etc. So, this is a good way to prove quality excellence. So, an independent external body evaluates the quality system and gives statement for accreditation, and this is the statement, or a sum of it, summary of it. However, if you have no accreditation, you should still have good management system. You should have comprehensive documentation. You should participate in inter-comparisons or proficiency tests, internal audits, or self-assessments. They are necessary. And a laboratory can request an independent external body to evaluate the laboratory. In Finland, this process is quite costly. I don't know the exact sums, but it is more than 10,000 euros to evaluate us. It's in fact a big process. Internal audits. About in your labs, are you doing internal auditations? Any comments? So I mean that some other units of your labs are evaluating your job. All right, but this is our standard procedure. We are doing this several times per year, and all areas. It also helps those that are making the auditation. If you are the guy who is doing the auditation to another lab, so it's like a learning process. It's a very good practice. So it gives you a look the work from different point of view. The best results are achieved when everyone involved are motivated and the attitude is positive. So it is also important not only the faults or errors, you should also document best practices. So, if you do nothing, you make no mistakes. However, we have to work and therefore mistakes happen. And human errors, I think they are perhaps the most relevant errors. Indeed. So, a lab needs a policy and procedures that define what to do in this case of errors. For example, if I make an error, I will certainly, in the next lab session, we have one internal lab session once per week. I will certainly, in those cases, explain what happened and then we think over what kind of things we should do to avoid this kind of error anymore. So it's not a good way to hide the errors. Not a good way. So, in case of mistake, it is important to observe, report, declare, make corrective actions, make preventive actions, and document the case. We are humans and errors happen. That's the case. We have to tailor our processes so that all these things that I explained in these presentations should be considered. All right, this was my last slide. I thank you very much for listening this. This might be or might sound quite boring area, but this is very, very, very important area. I think one of the most important areas.